Additional funding from Roger and Vicki Sant.
In the darkness of space, there are violent forces at work. Cosmic rays shoot across the universe. Asteroids billions of years old stream towards Earth. And solar winds wreak havoc. Their destination, the edge of space. Our upper atmosphere. It's Earth's first line of defense against the hurtling space rocks that we see flare into brilliance as meteors. A protective buffer against the high-energy solar wind that creates the beautiful northern lights. And crucially, it's a key link in a global electric circuit that blankets the planet from pole to pole. Far below, the surface of the Earth is hammered by 8 million bolts of lightning every day, up to 100 strikes every second. Most lightning strikes from the clouds towards the surface of the Earth. But occasionally, the most powerful bolts are accompanied by a ghostly and fleeting flash above the clouds, reaching all the way to the very edge of space, but lasting only milliseconds. It's been a decades-long challenge to understand these mysterious bursts of light. Now, from the high vantage of the International Space Station, it may finally be possible to capture images of these rarely seen events in the boundary between Earth and space. But what defines this region? Earth's atmosphere is a thin blanket of gas. The troposphere is the lowest and densest layer. All of life as we know it depends on this relatively thin, 5 to 10 mile thick band of protective air. Its thickness varies with latitude and the seasons. This is where most weather occurs, including the towering thunderclouds that generate lightning. A high-altitude helium-filled balloon ascends quickly through this region and enters the stratosphere, where most jet planes fly, and where the ozone layer is found, which absorbs the sun's ultraviolet light that can damage living things. Moving into this hostile environment, the air pressure drops, causing the balloon to expand. Up here, the lack of oxygen would quickly kill a person. The stratosphere reaches an altitude of about 30 miles. Eventually, the balloon cannot rise any higher. But the ever-thinning upper atmosphere, including the ionosphere, extends another 500 to 600 miles, even beyond the orbital height of the International Space Station, which circles Earth at an altitude of between 200 and 270 miles. From here, the ISS looks down on the planet. At this altitude, the environment is instantly lethal. The extremely low pressure would cause a person's body fluids to vaporize in seconds, while the little air that remains can reach temperatures of more than 2,000 degrees Fahrenheit. There are also dangers of radiation exposure in this forbidding atmosphere. But safely aboard the ISS, an international team of astronauts lives and works, including on this mission, Satoshi Furukawa, a native of Yokohama, Japan. An ardent baseball fan, he takes advantage of zero gravity to play a solo game. A medical doctor, one of Furukawa's jobs on the station is to study the effects of microgravity on the human body. He often conducts research as both doctor and patient. He's also the mission photographer. Using an extremely sensitive high-definition camera, Furukawa will capture nighttime images of Earth's upper atmosphere. The ISS is an ideal platform to study the edge of space, thanks to the cupola observation window. It offers a priceless view of space and the planet below. Its heavy shutters open to reveal windows for photography and viewing. It's from here that Furukawa will aim his camera when the station's orbit takes it into the Earth's shadow, which it passes into about every 90 minutes as it orbits the planet. Designed to capture never-before-seen phenomena, it's so sensitive that it can shoot color images in near total darkness, bringing to light places once hidden by the blackness of space. He's hoping to capture images of an elusive and mysterious form of high-altitude lightning, only recently discovered and still little understood. The story of these strange lights in the sky began one night in 1973, when a U.S. Air Force pilot named Ronald Williams was surprised by an unusual sight.
There was a typhoon over the South China Sea. I happened to be flying over the typhoon. And as I was going right towards the center of the typhoon, there was a big thunderstorm just off the center of the typhoon. All of a sudden, just by accident, I was watching it, because if I'd have been doing anything else, I wouldn't have saw it.
Williams saw a bolt of lightning go straight up from the top of the clouds.
When it came up, I happened to be watching it, and I just watched it go up. I reported it, and nobody had believed me. They said lightning don't go straight up. Has a discharge on something.
But it turned out that Williams was not the only pilot to see lightning emerge from the top of a cloud and shoot upward towards space. As sightings accumulated, they became a part of aviation folklore, rare and unconfirmed events that hovered just outside the boundaries of real science. Until another chance sighting provided more evidence.
A fellow by the name of Jack Winkler had some detectors out. He was looking for something else, but he discovered them by accident with equipment that was operated on dark nights in Minnesota.
While testing a low-light video camera in 1989, Jack Winkler and a team at the University of Minnesota accidentally captured a black and white image that seemed to show the elusive upward lightning the pilots had described. Fittingly, this ethereal phenomenon became known as a sprite, a whimsical name that captures its fleeting nature. These giant pillars of light sparked an intensified interest in lightning and the dangers it presents to spacecraft during launch or landing. Today, astronaut Satoshi Furukawa is looking for thunderstorms. Sprites are only found where lightning is present. But spotting sprites isn't easy. They only accompany bolts of lightning over 10 times more powerful than normal lightning. In 10 minutes, it will be nightfall again. So Furukawa quickly prepares his camera.
Recorder power is on. Monitor is on too.
This specialized camera should be able to capture images of the elusive sprites, even in these low-light conditions. He'll need this extra sensitivity to catch a sprite. If any sprites appear, they'll be above powerful bursts of lightning. Across the world, over 2,000 lightning bolts flash every minute, and over 20 million strike the US each year. They're 4 to 5 times hotter than the surface of the sun. And the most potent can discharge up to 1 billion volts of electricity. Unlike the superheated lightning flashing below the storm clouds, the sprites above are huge, but electrically much weaker and faster. disappearing on average in less than 70 milliseconds. Furukawa maintains his vigil for several hours, but without much luck.
It's difficult.
His camera recorded a huge number of lightning flashes, but no sprites appeared above them.
I felt like a hunter. It was impossible to predict where it would appear.
Though the search is frustrating and difficult, he's determined to capture a sprite. In part, because of a letter he received during training for his ISS flight. The letter was from an Israeli lightning expert, Yoav Yair, who wrote to inquire about the mission. He enclosed a photo of Ilan Ramon, Israel's first astronaut and a crew member of the ill-fated Columbia mission. Ramon had brought with him a high-sensitivity black and white camera to try to capture images of sprites from space.
And it's a big day for the Israeli science community.
Ramon's partner in the research was Professor Yoav Yair.
I asked him, please bring me one sprite image. He said, don't worry, I'll get you a couple.
After capturing over 9 hours of thunderstorm footage on board, he succeeded and transmitted several images of sprites back down to Earth. But tragically, Columbia never made it home. It disintegrated upon re-entry. Though debris was scattered widely, the camera that Ramon had used to capture sprite images somehow survived, with some of Ramon's work intact. One image of active lightning over Central Africa shows a bright flash of light above the lightning and arcing up towards space. It was a sprite. Ramon captured images like this one from several vantage points in orbit. Yair and his research team studied these photos and were surprised to discover how frequently sprite events occurred over large tropical storms and how widely distributed they were. But there was still much to learn. Yair saw Furukawa's mission as a great opportunity to advance the understanding of sprites.
It's so touching. I can feel their passion. I was there at their scheduled landing spot and looking up the sky. The Columbia never came back. They were my friends and my colleagues. I was very sad to lose them. At first, it was difficult to get back on track. I didn't feel like doing anything. Then I thought, we must take over their work and move forward. I thought that was the survivor's duty. So I am honored and happy that I was given this chance in this way.
So nearly 250 miles above Earth, Furukawa is working hard to further Ramon's legacy. He readies his camera as the flight path takes him towards Europe and into the nighttime darkness, Earth's shadow. He won't have much time. At ISS speeds, traveling over Paris to Rome takes just 2 minutes. Looking down, he sees the lights rimming the boot-shaped peninsula of Italy. In 10 minutes, he'll be over Central Africa. Weather patterns and topography make this the world's most lightning-prone region. Because it's estimated that only 1 in 10,000 lightning bolts produces a sprite, Africa's very active skies make it one of the best places to spot one of these elusive events. So the first step in capturing a sprite is to track the kind of extraordinary monster thunderstorms that produce superbolts of lightning. And figuring out where they might be is Yoav Yair's job.
Okay.
He analyzes weather patterns on the ground and sends the locations of potential sprite-producing thunderclouds to Furukawa on the space station.
This is a very exciting and emotional thing for me to do because it reminds me of the things that we did for Ilan Ramon and the crew of the Columbia in 2003.
With Yair guiding him, Furukawa circles the globe looking for the kind of monster thunderclouds that could produce a sprite. Then, while flying over the Middle East,
Incredible.
he sees something. It's clearly a sprite flashing over the thundercloud and surging towards space. And it looks like a color version of the one captured by Ilan Ramon from the Columbia Space Shuttle. It's the first clear, high-definition color photograph of a sprite taken from above. And there are more. Ahead is Taiwan, Japan, and mainland China. A giant sprite appears over Beijing, near the horizon. The white flash below is an unusually powerful bolt of lightning. The sprite above is far off. It may not look especially large, but some sprites can be almost 40 miles in height, dozens of times taller than ground-striking lightning bolts. Altogether, Furukawa captured 6 sprites.
It was a real surprise to me. It's so exciting when something previously invisible to us finally starts to become visible.
The footage was sent to Yoav Yair and an international team of sprite researchers who are continuing the work of Ilan Ramon and the lost Columbia crew.
Very nice. Great. Now it's much more detailed, better camera, color. We only had black and white, but it was really exciting for me. Actually, it really moved my heart to see it. I have to imagine this because they are all not with us, they're all gone. But I'm sure that if he knew that their mission was accomplished 8 years later, and maybe even going on later, they would feel fulfilled. He would be proud, I think.
Images like these are helping scientists to understand how a huge storm can generate sprites. During a thunderstorm, electric charge builds up in a thundercloud, causing lightning to emerge from the lower part of the cloud and strike the Earth, discharging an immense electric current. But if that lightning bolt is powerful enough, it can trigger a sympathetic spark above the cloud.
As you go up in altitude, the density of air decreases. And so low-density air is easier to make a spark in than high-density air. So a sprite is really caused by lightning down in the lower atmosphere that exerts a stress on the upper, thinner atmosphere and causes a spark up there.
And that spark gives rise to a sprite. As the scientists examine the images, there's one that attracts a lot of attention. Captured in one of Furukawa's pictures, the top of one of the sprites seems to reach all the way to the air glow layer. The air glow is part of the ionosphere, which is a vast sea of electrically charged particles, or ions. It's these particles, with help from the sun, that create the glow.
Air glow is due to solar radiation at short wavelengths, ultraviolet wavelengths, UV, the same stuff that sunburns us if we're outside without our sunblock, or X-rays, that we use to image our bones, and that can transfer energy to the molecules in the atmosphere, and that energy transfer causes a glow.
But the most important thing about the air glow may not be why it glows, but where it's located. It's the lowest part of the ionosphere, the uppermost region of the atmosphere. It begins about 60 miles above Earth and extends over 600 miles to the very edge of space. The air glow is just the most visible component of the ionosphere, which is created by radiation from the sun interacting with the topmost layer of Earth's atmosphere. So the image of a sprite reaching the air glow shows the incredible heights these massive sparks can reach. But these stunning images from the space station still leave many questions unanswered. How exactly do sprites form, and what accounts for their peculiar shape? To answer these questions, the group decides to try something that's never been done: to fly closer to sprites and to photograph them simultaneously with 2 different cameras on 2 different airplanes, hoping to combine these images digitally and reveal the anatomy of a sprite. The planes will also be equipped with the same super-sensitive color HD camera Furukawa has been using on the International Space Station. But their real secret weapon is a high-speed black and white camera that shoots 10,000 frames per second under low-light conditions. It will be able to show the formation of sprites in slow motion.
It will be the first time that we've had 2 aircraft simultaneously trying to image sprites with high-speed cameras. So it's very exciting for us.
They chose the area where the Great Plains meet the Rocky Mountains as a likely place to hunt for sprites because it's famous for very big nighttime thunderstorms. You can see huge thunderclouds there in the summertime. The weather is sunny almost 70% of the year. The intense sunlight heats the ground and causes a strong upward air current. This, in turn, creates active thunderclouds one after another, producing lightning. But only the biggest lightning flashes of all produce sprites. And once again, it will be Yoav Yair's job to help the team in the air find those huge sprite-producing thunderclouds. He and his team will be at the Yucca Ridge Field Station, a weather observation facility on the Great Plains north of Denver.
Oh, now you got it.
No,
You got it okay.
They will forecast where a sprite might appear and direct the planes.
All right.
At 5 p.m., the flight team gathers to discuss strategy for tonight's mission. They call the control station. Scientist Jeff McHarg, who will be on one of the planes, is asking for the lightning forecast.
We were just looking at the charge moment change map and then the weather map.
But it's not weakening, and the good news is it's moving into some extremely unstable air.
Walt Lyons of the Yucca Ridge Field Station is working with Yair to analyze the weather data. In this satellite image, clouds are shown in blue. That day, thunderclouds were developing in a variety of places. But would they produce powerful enough lightning to produce sprites? Back at the airport, the pilots talk among themselves. Usually, they avoid big storms, but tonight, they'll have to fly in and around the thunderclouds, hunting for the perfect position to capture sprites. They know it will be a rough and difficult flight. As soon as it gets dark, thunder begins to reverberate around the airport. The researchers board the planes on what looks like a promising night. At 9 p.m., the 2 jets take off. They're heading for thunderclouds 120 miles away that are vigorously producing lightning. The cabin is in constant communication with Yair and Lyons at Yucca Ridge.
Essentially, they want some kind of a central location.
He evaluates the data and gives the pilots the latitude and longitude of large thunderclouds where sprites might appear.
For reference, we'll be on this data collection run for about 10 minutes.
Outside the window, they see a huge thundercloud begin to glow with lightning.
Oh, it's here. Lightning. Quite promising.
Somewhere in the darkness above the cloud, they are hoping a sprite will occur. The high-speed camera is adjusted slightly upwards to shoot the area above the flashing thunderclouds. Jeff McHarg, who has spent 20 years chasing sprites, can barely contain his excitement. But Yair and Walt Lyons on the ground can see an unexpected change in the thundercloud.
They are here, and if they go like this, they would get this part. But
Yeah, both of them are starting to weaken.
The large thundercloud that was expected to grow has started to split in two. They've been in the air for 5 hours, with no sign of those elusive sprites. And now, the lightning is quickly losing momentum. Despite the promising forecast and their careful preparation, they have no choice but to return to the airport, defeated.
It was horrible. Yeah. I've seen much larger storms, you know, where you get really large sprites that happen pretty often, and this was just too small.
We'll see. Fingers crossed for the next one. Good night. Good night, everybody.
They realize this will not be easy. On the 4th of July, while people all over America are celebrating, the Sprite team hurries to the airport. They've been waiting for the right kind of weather for a week. Finally, new storm clouds powerful enough to generate sprites have appeared.
So if we go like here,
If we don't see lots of sprites, and this starts to get more intense, then I may want to extend up. We should just
go as soon as they get ready, I would say. Yeah.
Both planes take off into a stormy sky. While Denver watches fireworks below, they prep the cameras and get ready.
30 seconds.
They start to see flashes of lightning below. On the ground, Yair and Lyons are trying to figure out the best way to position the planes.
but then they would have to turn down, or do you want them to circumvent it?
Well, can they punch through and come around the other back?
Go all the way and
Up
then
to about 47 degrees and see if they can punch through it.
The two thunderclouds shown in deep blue have collided, and major cloud development has begun.
Yeah, maybe it's like...
They send the coordinates of the strongest lightning to the team in the air.
South of WPRT and new coordinates are WPRT. North 38 degrees, 20 minutes.
Outside, lightning flashes are everywhere. A monster cloud with a diameter of more than 300 miles is releasing electricity with frightening intensity. The scientists rush to position their gear. The frustration and anticipation of the previous week is getting to them, and tension in the cabin is high.
Sprite! Wow! That's a heck of a sprite there. Did you get it?
For an instant, a giant red flash appeared. On replay, they can see beautiful shafts of light thrusting upwards towards space. The mysterious sprite in all its glory. Then, the sprites keep coming. On board, the team reviews the stunning and unique images. This sprite was shaped like a mangrove tree. It's been captured in more detail than any sprite until now. Just like its name, this sprite evokes a fairy with wings.
Yeah, very big jellyfish. It's pretty. Very pretty.
It indeed looks like a jellyfish with many tentacles. sprites of many different forms appear, one after another. Seen up close, they have a variety of shapes. Eventually, a sprite appears that demands special attention.
This is spectacular.
The umbrella-like top of this sprite reaches an altitude of around 60 miles. That's the altitude of the airglow layer that appeared in Furukawa's footage from the International Space Station. The image confirms that sprites interact with the ionosphere. Now it's time for the high-speed camera. It's designed so that when a sprite is sighted and the button is released, the previous 3 seconds of footage will be saved. This is the momentary flash of a sprite taken by the super-sensitive camera. And when shot by the high-speed camera, it looks like this. In just a few hundredths of a second, countless particles of light rain down. This is the first time a sprite's formation has ever been revealed in such detail. During the night, 14 sprites were captured by the high-speed camera.
8,000, yes, very good.
What else will the footage reveal? With great expectations, they return to the ground.
Not too bad, huh? That's amazing.
It was fabulous. It was amazing. I haven't seen anything like that ever.
The long night is over, but they know their work is just beginning. Back in Denver, the team gathers to make some scientific sense out of their spectacular sprite footage.
The halo above and the elf below, and that's just because it's expanded out in front. Right.
At first glance, this sprite may seem to burst up from the storm clouds towards space. But when seen by the high-speed camera, the movement looks completely different. Bursts of light appear out of the center, spreading both up and down. In fact, when examined in slow motion, it appears that sprite formation is more complicated than early reports had indicated. And what about this sprite shaped like angels' wings? With this one too, bursts of light suddenly appear out of darkness. They go down, and the next moment up, and then down again. They change their direction as they unfold. So what is really happening? Within the sprite, electrons are colliding with charged particles in the atmosphere, creating a pathway for the electrons to travel. Where they go depends on the concentration of electrons and the composition of the atmosphere. Sprites are beautiful and intriguing. But do they actually have a role to play in Earth's upper atmosphere? Yukihiro Takahashi is investigating the aftermath of a sprite. Once the electrons cut open a path, the atmosphere around it becomes highly electrified. Following the sprite's path, a large electric current continues to flow from the thundercloud to the ionosphere, which shows up as the airglow in many sprite images.
The sprite flashes only for an instant, but at the moment when it flashes, a conductive path is created. The electrified path doesn't disappear when the flash ends, but stays there for a while. The effects are thought to last several seconds to minutes.
The result is a massive transfer of electric charge in the space between the cloud and the ionosphere. The team also successfully captured a sprite from different angles, as they had originally planned, using high-speed cameras placed on the two aircraft. By combining the images from the two cameras, the three-dimensional structure of the sprite becomes apparent. A large number of electrons collide with the atmosphere, creating brilliant bursts of light and opening channels where the electrons can flow. Each sprite channel can be hundreds of yards wide. A sprite event is like a switch that turns on an electric current in the space between the Earth and the ionosphere. In fact, our planet is surrounded by electric current, from the surface to the edge of space. Like lightning, sprites help to complete a global circuit, allowing charge to flow continuously around the Earth. But sprites reach much farther than lightning. And unlike lightning, sprites can transfer charge into the ionosphere, to the edge of space. Not only that, but the bolts of lightning that create the sprites are so powerful that they literally reverberate around the world.
When a sprite occurs, the parent lightning that causes the sprite radiates electromagnetic waves. Those waves propagate in what we call the global circuit.
Earl Williams of MIT studies sprites from this remote laboratory in western Rhode Island. Williams and his equipment are nearly off the grid out here, but they're completely plugged into the biggest circuit of all, the global electric circuit.
We've been monitoring this phenomenon for nearly 2 decades at this site, trying to look for long-term trends.
In fact, scientists have actually been measuring the global electric circuit on this unusual site since the 1950s, when the lab was set up by Williams' predecessor, Charles Polk of the University of Rhode Island.
The antenna immediately behind me is Charles Polk's. The more distant antenna is one that we constructed when Polk's antenna was struck by lightning and blew the antenna into many separate fragments all over the meadow we're sitting in right now.
Williams got involved with early sprite research by collaborating with Walt Lyons of the Yucca Ridge Field Station.
Every time Walt saw a sprite in Colorado, which is roughly 2,000 miles from here, we would see a big disturbance here in Rhode Island.
The antenna Williams is using measures a very low-frequency wave, like a steady hum, that resonates between the Earth and the ionosphere.
When a sprite occurs, the lightning that causes the sprite sends waves in that thin cavity around the world 2 or 3 times. And it is exciting something called the Schumann resonances. And the Schumann resonances is a manifestation of what we call the AC global circuit.
Earl's aunt was a prominent violin player, so it's not too surprising that he thinks of it in musical terms.
The vibration of a violin string is very much like what happens with Schumann resonances. We have a fixed string length, and there's one wave on the string which has a fixed frequency, say the A note of 440 hertz. For Schumann resonance, we have a fixed length, but the length wraps itself around the world. And for that fixed length and the speed of light, we have a fixed frequency of 8 cycles per second. So they're both examples of resonances, this one being a mechanical resonance, that one being an electromagnetic resonance, but the same wave phenomena applies.
It's almost like the music of the spheres, or of the Earth at least.
No matter where you are on Earth, if you have an antenna, a vertical antenna, like the one behind me, you will see an oscillation on that antenna at roughly 8 cycles per second. And that is maintained continuously by all the lightning on the planet. Every time there's a lightning flash, a small fraction of the energy in that lightning flash feeds into this global resonance.
The Schumann resonance is present all the time. It never dissipates because there's always lightning someplace on Earth. And when a sprite is produced by a superbolt of lightning, there is a spike in the Schumann resonance signal.
Every sprite lightning is a bell ringer for the Schumann resonances. One of these giant lightnings will single-handedly excite the whole Schumann cavity with electromagnetic waves. And everyone on Earth who has a receiver in the range of frequency of 8 cycles per second will detect a sprite event. Here on the oscilloscope, we have an example of the Schumann resonance signals. You can see the characteristic 8 cycle per second oscillation continuously. That's called the background Schumann resonances. Occasionally, you'll see a big increase in the amplitudes. Those events are the events that make the sprites. These are the lightning flashes, the very energetic lightning flashes that create sprites in the thin upper atmosphere.
Earl's science may be cutting edge, adding to our understanding of planet Earth. But his equipment is a little bit old school.
Because the Schumann resonances oscillate at only 8 cycles per second, it is kind of a low-tech operation here. I mean, we do digital recording of the signals, but you know, these are very low-frequency signals you can put on an oscilloscope, and you don't need high bandwidth equipment to record them. But you have to be in a quiet place. You can't do this in the middle of a city. There's too much background noise. And that's why we're out here in this very beautiful site in the middle of nowhere.
And super powerful lightning produces not only sprites, but other weird phenomena as well.
There are actually a whole zoo of creatures up there that are caused by lightning. There's something called an elve, and it's like a pancake of light within the airglow layer, and it's caused by the radiation field from lightning. Then there is a halo, which is also a pancake shape, but at somewhat lower altitude. And then there are blue jets and pixies and a whole host of other optical phenomena that occur in conjunction with lightning flashes.
Since the Schumann resonance fluctuates slightly depending upon factors such as the temperature of the Earth, Williams thinks it's one important way of measuring the health of the whole planet.
It's a natural setup for looking at the entire Earth. You have one quantity which represents the entire planet. And it's hard to dream up another such circumstance. It is like taking the EKG of the planet.
The global electric circuit surrounds everything on Earth and connects us to the edge of space. Sprites feed into the ionosphere from below. But from above, the sun also affects the ionosphere, resulting in the vivid displays of the aurora borealis. Auroras are light displays caused by the collision of charged particles streaming from the sun into our atmosphere. There are two types of auroras. The discrete aurora, like the northern and southern lights, have well-defined boundaries that can be seen with the naked eye, and diffuse auroras that spread out over a wide area and are less colorful. 93 million miles away, auroras are born from a landscape of blistering temperatures and violent eruptions. From the surface of the sun, huge volumes of solar material in the form of charged particles are blasted into space. A fleet of satellites monitors this solar activity. Stereo A and Stereo B satellites are making 3D images of the sun and also tracking solar activity. These eyes in the sky paint a detailed picture of the sun and the powerful forces erupting from its surface. The constant stream of charged particles The solar wind is so violent, it would strip away the Earth's atmosphere if it hit our planet directly.
The sun you can think of as a really big, angry hairdryer in a lot of ways. It's constantly blowing hot, energetic wind out in all directions, not just directly towards the Earth, but in all directions. And this hot, energetic, fast-moving particle stream hits straight on with the Earth.
Earth's magnetic field blocks and deflects the solar wind, protecting our planet from a full-on assault. But there is a back door that allows some of the charged particles from the solar wind to reach us. In the Earth's shadow, there is a region in space where charged particles accumulate. These particles, though drastically decreased in number, sneak in through small gaps in Earth's magnetic defenses. The charged particles dash toward Earth and interact with the magnetic field, which deflects and diverts them to the poles. They rain down, forming luminous rings in the sky. The beautiful, vibrant colors of the aurora are visible evidence of the particles' interaction with Earth's second line of defense, the atmosphere.
The aurora are different colors at different altitudes, depending on the gases in the atmosphere that the particles are interacting with. So it's red at higher altitudes, it's oxygen, and then blue and green, oxygen and nitrogen, as it gets denser into the atmosphere where the gases get thicker. And then for really, really strong interactions of the particles, energetic particles really penetrating deep into the atmosphere, you may even see like a pinkish purple color down at the bottom where there's more nitrogen.
But sometimes, things can go wrong, really wrong. Sometimes the blast of charged particles can be so intense that the auroral ring thickens and vibrates explosively.
There are these periodic events, these coronal mass ejections, where the gas just is incredibly more intense than it normally is, and this charged particle cloud will come out, spiral out towards the Earth, and our magnetic field will respond.
The Earth's magnetic field does a good job of protecting us. The more beautiful the aurora, the more intense the battle at the edge of space. And even satellites high above Earth can fall victim to the power of our sun. In 1989, during a period of intense solar turbulence, induced electric currents caused by the aurora shut down the entire power grid in Quebec, Canada, in under 2 minutes. The province's largest city, Montreal, was crippled by power outages. Human activity throughout the region came to a halt for 9 hours. The more recent Halloween storms of 2003 caused hour-long power outages throughout Sweden and impacted satellites and aircraft communications. But the greatest solar storm on record took place in 1859. It created auroras so powerful, they illuminated skies as far south as Hawaii and Panama, while playing havoc with telegraph systems around the planet. A similar storm today could devastate power grids and communication systems and cost billions to repair. In today's wired world, no one is invulnerable.
Solar storms can affect satellite communications in different ways. Performance of your handheld radio, your GPS receiver, your satellite television receiver, your satellite radio receiver. All of these things can be affected by space weather.
We think of electricity as a modern invention. But the electric Earth has always been with us, surrounding our planet and connecting us to the edge of space.
This NOVA program is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS. NOVA is also available for download on iTunes.
Band. Up here, the lack of oxygen would quickly kill a person. The stratosphere reaches an altitude of about 30 miles. Eventually, the balloon cannot rise any higher. But the ever-thinning upper atmosphere, including the ionosphere, extends another 500 to 600 miles, even beyond the orbital height of the International Space Station, which circles Earth at an altitude of between 200 and 270 miles. From here, the ISS looks down on the planet. At this altitude, the environment is instantly lethal. The extremely low pressure would cause a person's body fluids to vaporize in seconds, while the little air that remains can reach temperatures of more than 2,000 degrees Fahrenheit. There are also dangers of radiation exposure in this forbidding atmosphere. But safely aboard the ISS, an international team of astronauts lives and works. Including on this mission, Satoshi Furukawa, a native of Yokohama, Japan. An ardent baseball fan, he takes it.
Additional funding from Roger and Vicki Sant.
In the darkness of space, there are violent forces at work. Cosmic rays shoot across the universe. Asteroids billions of years old stream towards Earth. And solar winds wreak havoc. Their destination, the edge of space. Our upper atmosphere. It's Earth's first line of defense against the hurtling space rocks that we see flare into brilliance as meteors. A protective buffer against the high-energy solar wind that creates the beautiful northern lights. And crucially, it's a key link in a global electric circuit that blankets the planet from pole to pole. Far below, the surface of the Earth is hammered by 8 million bolts of lightning every day, up to 100 strikes every second. Most lightning strikes from the clouds towards the surface of the Earth. But occasionally, the most powerful bolts are accompanied by a ghostly and fleeting flash above the clouds, reaching all the way to the very edge of space. It's hidden by the blackness of space. He's hoping to capture images of an elusive and mysterious form of high-altitude lightning, only recently discovered and still little understood. The story of these strange lights in the sky began one night in 1973, when a U.S. Air Force pilot named Ronald Williams was surprised by an unusual sight.
There was a typhoon over the South China Sea. I happened to be flying over the typhoon. And as I was going right towards the center of the typhoon, there was a big thunderstorm just off the center of the typhoon. All of a sudden, just by accident, I was watching it, because if I'd have been doing anything else, I wouldn't have saw it.
Williams saw a bolt of lightning go straight up from the top of the clouds.
When it came up, I happened to be watching it, and I just watched it go up. I reported it, and nobody had believed me. They said lightning don't go straight up. Has a discharge on something.
But it turned out that Williams was not the only pilot to see lightning emerge from the top of a cloud and shoot upward towards space. As sightings accumulate the advantage of zero gravity to play a solo game. A medical doctor, one of Furukawa's jobs on the station is to study the effects of microgravity on the human body. He often conducts research as both doctor and patient. He's also the mission photographer. Using an extremely sensitive high-definition camera, Furukawa will capture nighttime images of Earth's upper atmosphere. The ISS is an ideal platform to study the edge of space, thanks to the cupola observation window. It offers a priceless view of space and the planet below. Its heavy shutters open to reveal windows for photography and viewing. It's from here that Furukawa will aim his camera when the station's orbit takes it into the Earth's shadow, which it passes into about every 90 minutes as it orbits the planet. Designed to capture never-before-seen phenomena, it's so sensitive that it can shoot color images in near total darkness, bringing to light places one, but lasting only milliseconds. It's been a decades-long challenge to understand these mysterious bursts of light. Now, from the high vantage of the International Space Station, it may finally be possible to capture images of these rarely seen events in the boundary between Earth and space. But what defines this region? Earth's atmosphere is a thin blanket of gas. The troposphere is the lowest and densest layer. All of life as we know it depends on this relatively thin, 5 to 10 mile thick band of protective air. Its thickness varies with latitude and the seasons. This is where most weather occurs, including the towering thunderclouds that generate lightning. A high-altitude helium-filled balloon ascends quickly through this region and enters the stratosphere, where most jet planes fly, and where the ozone layer is found, which absorbs the sun's ultraviolet light that can damage living things. Moving into this hostile environment, the air pressure drops, causing the balloon to expand.